So we want to get rid of the king and turn king coin into community coin. The challenge is, given a certain number of nodes, good and bad, in a distributed network, how can we achieve agreement over the set of transactions? So, our kingdom is now organized in a distributed network. What does it actually mean? Well, we're just single entities. These can be persons or organizations. And we're independent, but we're all somehow connected to a network. Notice that not all the nodes are connected. By nodes, I just mean single points here, but generally there's high connectivity within this network. There are two main problems now to overcome to reach agreement in such a network. First, there are network imperfections, and thus there is no global time to reach consensus on. So let's assume we're currently updating the status of the ledger in our community. So everyone is broadcasting his current view on the ledger to everyone else. But because some of the connections are inexistent between some of the nodes, or are just slow connections, all the different nodes might have a different view of what the current state of the ledger should look like. And thus we might even have, in this case, 7 different views what the ledger should look like, and thus no agreement can be reached anyways, because everyone thinks it's something different. Second, there's anonymity. I mentioned this as a big plus in the section on digital identity and addresses. But in this case, to reach consensus, it can be disastrous if you have a bad actor in your network. Let's say you have one bad actor here in this community, in our kingdom. And this bad actor casts wrong information, faulty transactions onto the network. So there will be faulty information. The other ones are good nodes though. These are posting or broadcasting the correct information. Because there's only one now, we can still agree on the mostly good information. This works as long as we have the majority good nodes in our community. But here, because anyone can just create as many addresses as he wants to, and thus basically as many entities as he wants to, this bad actor could just create a bunch more addresses, connect to our network, and cast a lot more faulty information into our community, up to the point that we can't reach consensus anymore, or we even choose some faulty information to be the current state of the ledger. Let's look at a possible solution. We're going to implement the following protocol in our community. First, everyone broadcasts new transactions to all other nodes. Then each node collects new transactions into a block. So everyone starts creating blocks with whatever they hear from other nodes. Everyone does that. And then, the crucial point, in certain time intervals, a random node is chosen to propose the new block. Notice that we're not implementing a specific consensus protocol. We're not voting on the majority or anything like that. We just choose a random node and that one gets to propose the next block. So this might look something like this. We already have some information on our public ledger, on our community coin ledger. So we have here this blockchain structure, single blocks with transactions inside of them. Then we have the blocks linked with hash pointers. And we also have hash pointers between certain transactions. So we can go back in time and see where a coin actually came from. Okay, now let's say this node is chosen to propose the new block. So all it will do, it will append the block with all the transactions it heard about, link it to the previous one, and that's all that is. Lastly, other nodes are gonna accept or reject the new block by building on it or continuing on the previous one. So let's say we've chosen a good node here and it posted just valid transactions. So in that case, the next node that will be chosen then, if it is a good node, will continue this process, post its block, and link it to the previous one. But what if we've chosen a bad node here? Let's say we've chosen this one, and the bad node posted faulty information in this block right here. So let's say the current state is here. Okay, because all these transactions are also linked to previous transactions, all the other good nodes participating in the network can check what the faulty node actually posted here and easily detect if something is wrong. And if it is wrong, they will just then continue building on the previous block here. So if the next node chosen is then again a good one, it will post a block, but then append it here to the previous block. You might already get an intuition of how this type of system is going to work. It's only going to work if the majority of the nodes are good nodes. Otherwise, the probability of selecting a bad node might be too high, so that we might select bad nodes consecutive times and then we might be growing here the blockchain in the wrong direction with all the faulty information. So let's look at a few more implications of this first design proposition. Can a bad actor steal coins from someone else in our community? Luckily, that's impossible. For that to happen, the evil hacker man would need access to the private key of that other person, which is almost impossible to get. Next, what about denial of service attacks? That is actually possible, but it's not that big of a problem as long as the number of bad nodes is small. So let's say Alice and Bob really don't like each other, and Alice is going to be selected to propose the next block. So she's just going to erase all the transactions Bob posted. So his transactions will not be included in the next block. That's annoying for Bob, but he can just wait till the next block is going to be posted by hopefully someone else than Alice, and that person will include Bob's transaction. So he has just to wait a little bit longer to get confirmation. What about the double spending attack? Now that actually depends. Let's assume Alice wants to buy a car from Bob. And we already have some initial blockchain structure going on. And now Alice and Bob agree on some price for the car, and Alice proceeds to the checkout and wants to pay in our community coin currency. So she will use her digital wallet, pay at the checkout, which will broadcast her transaction out into the network that Alice wants to pay Bob, let's say 1,000 coins, and all the other nodes will register that and put that in the bundle of their current transactions they hear about. Then, let's say this node is chosen randomly, and it will append this new block to the existing blockchain. And this block will now include Alice's transaction that she wants to pay Bob 1,000 coins. So at this point, Bob can see that this transaction he got from Alice is confirmed by the blockchain. So Alice seemed to have sufficient funds to pay him. So Bob hands over the keys to Alice and she drives off. But how would a double spending attack look like now? For that to happen, Alice needs to be chosen to propose the next block. She's going to be happy about that, because she's thinking, oh well, let me try to buy 2 cars for the same money. So she will create a block, and she will quickly go to a different car dealer, to John, and she will buy the same car also for 1000 coin and create that transaction. So Alice pays John 1000 coins. Then she will append this new block to the previous block right here. When a split in the blockchain occurs like that, this is called forking. But will this double spending attack succeed now? Well, it depends if the blockchain continues to grow on this one or on this fork. How do we know about that? Well, the basic rule is to extend the longest chain. But in this case, we have two possible forks, both have the length of 3 blocks. Then the heuristic is to extend the block that was heard about first. But still, we could have, let's say, this node chosen and this node heard about this block first. So the node will continue growing the blockchain right here. And if that happens, here John also gets confirmation that his transaction is on the blockchain, and he will now hand over the keys as well. At this point, this fork becomes the longest chain and is the valid consensus chain. And this block here, with the transaction Alice pays Bob, is going to be orphaned and it's going to be invalid from now on. Because you can only have here one valid transaction. So this is going to be true according to the blockchain, and this is going to be false. Be aware that in technical terms, both of these transactions look exactly the same. So there's no way to somehow judge in technical terms if this should be better or this should be better to extend. In this case, it's just unfortunate that Bob already handed over the keys. So Bob gave away his car without getting payment for it. How could he prevent this from happening? Here's the proposition. He could wait just a little bit longer until the next few blocks are going to be appended upon the block that contains his transaction from Alice. So let's say there are 2 more blocks created and linked to the block with his confirmation. Why would that actually help? Well, let's see what Alice would have to do to attempt a double spending attack now. Well, first, she will be chosen, right? So she will create a block and create this alternative transaction to John instead, and append this block right here just before she paid Bob. Okay, so now if the next node chosen is not Alice, just by default, the chain will be continued right here and Bob's transaction would still be valid. So actually Alice needs to be chosen again. She would create just a valid block here. She needs to be chosen again to be able to append again to the shorter chain right here. And then at this point, it's kind of random if there would be a good node chosen, if we would continue building on here or here. Or maybe Alice even manages to get one more choice, so she could make this the longer chain, and then actually all the other good nodes would then after that also continue building on this new consensus chain, and this transaction to John instead would be the valid one, and this one would be dropped. But this is actually really hard to do, because assuming Alice has just one voice or one identity in the network, the chance of her being selected 4 consecutive times is really, really low. So to sum up, this new design circumvents the problem of network imperfections and allows us to reach some consensus on the blockchain. But the problem of anonymity remains. So we know that Alice can just create an arbitrary amount of identities in our system just by creating an arbitrary amount of public keys, and then she could just increase the chance of her being selected so that something like this here, like this type of double spending attack, is still feasible. So we need some way to prevent this type of sybil attacks. Also, what are the incentives? Why would anyone maintain the ledger anyway? This will bring us to mining.